Now that we're able to draw Lewis structures for molecular compounds, we're able to predict what shapes the molecules are going to take. And these shapes are important because the shape of a molecule will determine how it reacts with other molecules. The way we can predict the shapes is using VSEPR theory. What VSEPR is, or what it stands for, is valence shell electron repulsion. And although it has a long name, VSEPR, it's actually a very simple idea. VSEPR says that since electrons are all negatively charged, they will repel one another and therefore bonded atoms will move as far apart as possible. Remember that bonds, or covalent bonds, are made of two electrons, and therefore bonds repel each other as well. So the easiest way to see this is let's look at an example Lewis structure. So I'll draw the Lewis structure for ammonia, NH3. And you'll notice that when we've been drawing Lewis structures, I've been spreading out where the bonds are and the lone pairs. And the reason for this is that since all of these bonds contain electrons and the lone pair is made up of electrons, they all repel each other. So all of the bonds want to move as far away from each other as possible. And we can think of these electrons at the top, this lone pair, remember the electron clouds, the orbitals we talked about, as repelling as well. So this electron pair is going to want to get as far away from the bonds as possible. And since these electrons want to repel these negative charges, want to move as far away as possible from one another, we can actually fairly easily predict the shapes of different molecules based upon the Lewis structures. We can easily tell the shape of a molecule just by looking at the number of atoms and the number of lone pairs that are around the central atom. So let's look at the first few cases. These are the simplest of the shapes. So first, if we have two atoms that are bonded together with a covalent bond, there's actually only one choice for their shape. They don't have a center atom because you only have two atoms, and if you don't have a center atom, you can't have lone pairs on them, so that's not applicable. And the only shape that we can draw between two atoms is a line. Therefore, whenever you have just two atoms in a compound, it's going to be linear. And here's the three-dimensional representation of that. If now we add a central atom, we can now look at the number of atoms around the central atom. We have 2 atoms around the middle atom, so there's 2 atoms, and there are 0 lone pairs on the central atom. And in that case, we have a linear compound as well. These bonds, because they repel each other, try to get as far away as possible from each other. And because there's no other electrons here, they can get 180 degrees from each other. In the next case, we have 3 atoms around our middle atom. So we have 3 atoms around the center. We have 0 lone pairs on the center. In that case, the farthest these bonds can get from each other are actually 120 degree angles, giving us a triangle shape. If you made connections between the outer atoms here, you would get a triangle. And this shape is flat. It would lie flat in your hand if you held it. So we call it trigonal for the triangle and planar being flat. When we move on to 4 atoms around the center with 0 lone pairs, the farthest that these bonds can get from each other, now in the Lewis structure it looks like 90 degrees, but in fact they can get farther. They can get about 109 degrees away from each other in 3 dimensions. In this shape, if we connect all the outside atoms, we form what is called a tetrahedron. So we call this tetrahedral. We can keep going, and if we have 5 atoms around the center with 0 lone pairs in the middle, we call this trigonal bipyramidal. The reason is we have a triangle shape at the center of this molecule, and then we have 2 tips of a pyramid on either side. The last of the simple structures, the base shapes we can look at, has 6 atoms around the outside with 0 lone pairs on the center atom, and this is called octahedral. We can think of this almost as 2 tetrahedrons stacked on top of one another. Now let's look at a few that have lone pairs. So here we have a molecule that has 1, 2, 3 atoms on the center atom and 1 lone pair. Now the lone pair repels all the other atoms. So just like the bonds repel each other because they're negatively charged, so does this lone pair. So instead of these being spread out in that trigonal planar shape we saw before, they're going to be pushed a little bit farther away into this more pyramid shape. And I'll draw them in. Here are the lone pairs of electrons. They're up here, and they're basically repelling the other bonds away from them. And we call this trigonal pyramidal because it still has that triangle shape to it, but is in 3 dimensions. If we have 2 atoms on our middle atom and 2 lone pairs of electrons, we end up with a bent shape. So here I'll draw in the electrons again. Here are our lone pairs, and if they all repel each other equally or about equally, we end up with a bent shape. Now there are a lot of shapes, but let me show you a trick for figuring out these more complicated ones. So if I look at NH3, this molecule, let's ignore that I have a lone pair, and let's count how many things are around my atom, around my center atom. I have 1, 2, 3 atoms and 1 lone pair. That's a total of 4 things around my center atom. If I look back at my original shapes, well, what shape has 4 things around it? Well, that would be tetrahedral. And if I look at my 3-dimensional shape and I cover up one bond, cover up that one bond, what do I end up with? Well, what's remaining below where you see the laser pointer is the trigonal pyramidal shape. If instead I look at the bent molecule, I see that I have 1, 2, 3, 4 things total around the center. Again, 4 things around the center is tetrahedral. And now if I cover up these 2 with my finger, with the laser pointer, if you look at what's not being covered by the laser pointer, that's bent. So you can actually figure out how things look by going back to what they would look like if they had all bonds instead of lone pairs. The last 3 common geometries that we're going to look at also have lone pairs of electrons. The first shape we're going to look at has a total of 1, 2, 3, 4, 5 things around the center atom, so it's based off of the triangular bipyramidal geometry. If we cover up one of those 5 bonds and change it to a lone pair, we get what's known as a seesaw shape, because we still have a lone pair over here that's going to repel all the other bonds away from it. So here we have 4 atoms and 1 lone pair, and we get the seesaw shape. The last 2 shapes are based off the octahedral geometry, because both of them have a total of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 things around them. So if we cover up one of those bonds from the octahedral geometry, replace it with a lone pair, what we get is a square pyramidal geometry. We have a square shape as the base, and the pyramid is formed going to the top atom. The last one has 4 bonds, and 2 of the bonds have been replaced from the octahedral geometry with lone pairs. In that case, we get a square planar geometry, where the electrons at the top and at the bottom keep the atoms in the middle evenly spaced and in a flat shape, so it's planar. So let's look at all of these geometries together. And try an example. So I'm going to draw a Lewis structure, and let's see if we can figure out what its shape is going to be. So the first one I'll draw is H2S. Now when you draw a Lewis structure, you may not end up drawing it in the correct shape, which I purposely have not done because you don't know what the shape is until you finish the structure. So here we can see we have 2 atoms bonded to the center, and we have 2 lone pairs. So what has 2 atoms and 2 lone pairs? This is going to be bent. Here's another one. This molecule is CH2O. We'll look, well, we have, oh, I gotta complete octets. Oops. Okay, octets are now complete. So we have 1, 2, 3 atoms around the middle with no lone pairs. So that gives us a trigonal planar geometry. No, and we'll do one more. So let's do CH2BrCl. Here we have 1, 2, 3, 4 things around the center atom, no lone pairs, which would mean this is tetrahedral.